Welcome to this class. The previous lecture, we discussed the three methods of solving systems of linear equations, which are back substitution method, Gaussian elimination, and Gauss-Jordan elimination method. And we demonstrated how to solve a system in using back substitution method. And in this short video lecture, we are going to define what we mean by equivalent system, and then discuss how to transform a system that is not in Echelon form into Echelon form, and discuss the characteristics of a matrix matrices which are in Echelon form. So let's start by defining what we mean by equivalent systems. So a system, two systems of linear equations are said to be equivalent if they have precisely the same solution set. If they have precisely the same solution set. About the definition of equivalent systems, systems which have the same solution set. And so to solve a system, that is not in row echelon form, first transform it to an equivalent system that is in row echelon form by using the operations listed below. So the following three operations are the one that leads to equivalent system. So the first one so maybe you can just put in form of a theorem and then say theorem operations that leads to equivalent systems of equations. And so each of the following operations on a system of linear equations produces an equivalent system. System. So there are just three. One, interchange two equations. Number two, multiply an equation by a non-zero constant. And then number three, add a multiple of an equation to another equation. So those are the three operations on a system of linear equations that can produce an equivalent system that can help you to transform a non-row echelon form system to a row echelon form system that will help you to solve it by back substitution. So therefore now let's define what we mean by row echelon form of a matrix. So definition. Definition of what we call row echelon form. So REF of a matrix. So this is how we obtain a row echelon form matrix. So you say a matrix in row echelon form has the following properties or characteristics. So one, all rows consisting of entirely zeros occur at the bottom of a matrix, of the matrix. Of the matrix. So in case there is any row that has all the elements to be zero, then it must be at the base or at the bottom of the matrix. And then number two, for each row that does not consist entirely of zeros, the first non-zero entry is 1, called the leading one. So if there's any row that doesn't have all the elements to be 0, then the first non-zero entry must be 1, called the leading one. And then number 3, for 2 successive non-zero rows, the leading one in the higher row or the top row is further to the left than the leading one in the lower row. So that's the third characteristic. And then just a remark, if all these properties if our matrix in row echelon form is said to be in reduced row echelon form, that is RREF, if every column that has a leading one has zeros in every position, above and below its leading one. So let's give some examples to illustrate matrices which are in row echelon form, those which are in reduced row echelon form, and then those ones which are not in row echelon form. So maybe even before we give the example, we should, from this remark, I should say that a matrix that is in reduced row echelon form, the first condition for it to satisfy, it must be in row echelon form. So examples of matrices in row echelon form. So we have a matrix A given by this 1, 2, -1, 4, 0, 1, 0, 3, 0, 0, 1, and -2. This is in row echelon form because these are our leading ones. And see, in our leading one, so if you consider 2 consecutive rows, then the one on the upper row is to the left of one of the lower row. like this is to the left, this one, similar, this one is to the, this one is to the left of this other one here. And then B, if we have a matrix 0, 1, 0, 5, 0, 0, 1, 3, and 0, 0, 0, 0. Also, this is a matrix in row echelon form because you see this is the leading one, this is the leading one, and then this matrix happens to have a row with 0 elements, and so all that row is to the bottom of the matrix here. So that's an example of matrix in row echelon form. And then C, 1, -5, 2, -1, 3, 0, 0, 1, 3, -2, 0, 0, 0, 1, 4, and then 0, 0, 0, 1. Zero, 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 1. So this matrix is also in row echelon form because you see this, the first non-zero elements in each row is 1. And if you consider consecutive rows, then the 1 on the upper row is to the left. And then D, if I have this matrix D given by 1, 0, 0, -1, 0, 1, 0, 2, 0, 0, 1, 3, 0, 0, 0, 0. Then this is also in row echelon form because you see these are the leading non-zero elements and they are ones, and it happens to have a row that has all the elements 0, so it's placed at the bottom. And then, so these are the examples, or I can have another one, matrix E. If I have E of this form 1, 2, 8, 0, 1, 4, 0, 0, 1. This is also in row echelon form because these are my leading ones. And when you consider consecutive rows, then leading one on the upper row is to the left. Or I can have this other example, F, if I have 1, 0, 9, 4, 0, 1, 2, 8, 0, 1, 0, 0, 4, what 4? I have 0, 1, 6, and then 0, 0, 0, 1. Then this is also an example for matrix in row echelon form because the leading elements in each row are ones. So you see this, and when you consider consecutive rows, 1 on the upper row is to the left of the lower row. Now I want to use the same examples to illustrate. So this to the left is non examples, and then I want to give examples of non row echelon form matrices. Now you see, like for this one here, if I call A1, so what I'm writing in blue here, they are non-row echelon form matrices. So if now I say I put here 0, 0, 1, -2, and then I write here 0, 1, 0, 3, and then I write 1, 2, -1, 4. Then this is a matrix. This matrix is not in row echelon form because you see if you compare, so these are the leading ones. These are the leading ones in each row. And you see, like this first row and the second row, the leading one of the first row or the upper row is to the right of the leading one to the row at the bottom, which is not the case. The case is that leading row of upper element must be to the left. So this positioning of this leading ones is what makes this one not be in row echelon form. And then if I have this example, if I call this matrix B1, if now I have 0, 0, 0, 0, and then I have 0, 0, 1, 3, 0, 1, 0, 5, then this matrix is not in row echelon form because of several reasons. First reason is that it has a row that has all the elements to be zeros and it's at the top. That should not be the case. A row that has all the elements to be zeros must be at the bottom. And also when you compare these consecutive rows, leading one on the upper row is to the right of leading one to the lower row. That shouldn't be the case. It should be the other way around, that this leading one of the upper row must be to the left of leading one of the lower row. If I have this matrix called C1, I have 1, -5, 2, -1, 3, and then I have 0, 0, 0, 0, 1, and then I have 0, 0, 0, 1, 4, and then I have 0, 0, 1, 3, -2. This is also not in row echelon form because like this leading one, this another leading one, these are the leading ones. So if you compare the leading one on the second row and the third row, leading one on the second row is to the right of the leading one of the third row. That shouldn't be the case. This leading one of the upper row must be to the left of leading one to the lower row, similar to the third and fourth rows. And you can also give a known example, like for D, if you say I have a matrix D1 given by 1, 0, 0, -1, and then 0, 0, 0, 0, and then 0, 1, 0, 2, and then 0, 0, 1, 3. This matrix, though if you compare the leading ones of the non-zero rows, they are always to the left. The upper one is always to the left of the lower one, but it has a 0 row or row with all the element zeros, which is not at the bottom. So this is a problem. This is what makes this one not be row echelon form, because it must be at the bottom. And then I can say if I have a matrix E1, E1, I have 1, 2, 8, and then I say 0, 0, 1, and then 0, 1, 4. Then this matrix is not in row echelon form because now when you consider the second and the third row, the leading one of the second row is to the right of the leading one to the third row. That shouldn't be the case because second is on top, then the leading one must always be to the left. So this is the problem. And then if you say F1, we have 1, 0, 9, 4, and then say 0, 0, 1, 6, and then say 0, 1, 2, 8, and lastly 0, 0, 0, 1. This matrix is not in row echelon form because if I just consider this as the leading, this is the leading, this is the leading, and then this is the leading. The second and the third row is the one that makes this one not be in row echelon form, because the leading one of the second is to the right of the leading one to the third one. So that should be the case. Now, for these examples we have given, you see B, we said B, matrix B is in row echelon form. Also, when you consider the columns with leading one, you see this is 0, this is 0, this is 0, this is 0. So this matrix B is also in reduced row echelon form, because every column is already in rational form, and also the column that has leading one has zeros in other positions. Similarly, this matrix D is also in reduced row echelon form, because every column that has leading one has zeros in all other positions. You see, these are zeros, these are zeros, these are zeros. So also D can be said to be in reduced row echelon form. Another example of reduced row echelon form matrix, we can have, say, matrix A given by 1, 3, 0, 1, and then I have 0, 0, 1, 8, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is also in reduced row echelon form, because already the leading ones, these are the leading ones, and in all those columns, other positions are taken by zeros. I can have another matrix, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 1. This also in reduced row echelon form. So just note, reduced row echelon form implies row echelon form, but row echelon form does not imply reduced row echelon form. Does not imply reduced row echelon form. Good. So that's how you specify matrices in row echelon form and reduced row echelon form, and you can always give some known examples. So in the next video, we'll be now describing the second method of solving systems of linear equation. That's the Gaussian elimination method. Thank you.